that in this other paper, a collection of data taken from this paper by Roberto Maiodino, but again, this has been confirmed by other independent studies of the position of these newly detected black holes in the black hole to stellar mass plane. And you see here the local scaling relation. And you see that most of these data show that the black holes are overmassive at a given stellar mass with respect to the locally expected correlation. Of course, we know that there are several uncertainties related to the black hole mass determination, but taking this at face value, it means that you have, a fast and early growth of black holes at early cosmic times. I will try to argue that early dust somehow connects this to evidence of a mature universe or a rapidly evolving universe at high redshift. So let me first focus a bit on this piece of evidence of an overabundance of UV luminous galaxies at redshift larger than 10. We know that, the literature has been showing a lot of activity on trying to provide different information for this finding, which go from the failure of the lambda CDM model to a changing nature of the stellar populations in these high redshift galaxies, to higher star formation efficiencies or bursty star formation, and little or no dust contact. Okay, and so I will focus first on the changing nature of stellar populations. So what are the properties of stellar populations that you expect to inhabit these high redshift galaxies? In general, if you look at the SED, so the modeling of the spectral energy distribution of these high redshift sources, generally the model suggests relatively low metal content, but not ultra metal poor content, something on the order of 10 to the minus 2, 10 to the minus 1 solar, and young ages. And theoretical models have been showing us that at redshift larger than 10, with these physical conditions, you would indeed expect peculiar physical properties for the stellar populations. And to give you an example of this, I show here the results of a set of simulations with very high resolution done by Soo-Myung Chon, where he's essentially interested in understanding what is the emerging stellar mass distribution from star clusters forming at very high redshift under different metallicity content. Okay. And so here it's very complicated, so I will not be able to show you all the details, but what you see here is the projected gas density after 10 to the 4, 10 to the 5 years since the onset of star formation. In each panel, you see the result of the simulation with different initial metallicity. So this is the highest metallicity case, and this is the lowest metallicity case. And in yellow, you have stars with masses larger than 1 solar mass, and white points show stars with smaller stellar mass. And even by eye, you clearly see that as you go to lower metallicities, the number of white points disappear. So you have most of the stars forming with relatively high masses. And of course, you then can quantify this by doing a histogram of what is the mass function at the end of the simulation. And this is shown in this plot here with, again, in each column, you see a different metallicity from 10 to the minus 1 solar to 10 to the minus 4 solar. And in different lines, you see different redshifts. Okay, so he has repeated the same experiment going from redshift 0 up to redshift 20. And probably you cannot catch this by distance, but you have this diagonal line here, which is the slope of the present day IMF. Okay, and you can maybe see that there is an axis at high stellar masses as you go to lower metallicity, and for a given metallicity as you go to higher redshift. Okay, and this is essentially due to reduced cooling ability of the gas which favors more massive star formation, and through the growing temperature of the CMB, which somehow prevents cooling below a given temperature, favoring, again, more massive stars to form, okay? So if you want to summarize this, you see this, you can quantify the fraction of stars in the massive component, in the top-heavy component, with masses larger than 10 solar masses. And in this plot, you see with this fraction as a function of redshift for different metallicities. And so you see that the fraction increases with increasing redshift at a fixed metallicity, and it increases with decreasing metallicity, okay? And overall, what you find that at redshift larger than 10, more than 40% of the stars are in this top-heavy component. So this is purely based on theoretical findings. So you expect a deviation in the IMF, in the standard IMF, as you go to higher redshift, even for relatively metal-rich 0.1 solar in terms of what you expect in the high redshift universe can be considered metal-rich at high redshift. So what we decided to do is to go from this theoretical expectation and try to work out what would be the consequence of this in terms of the UV luminosities of these high redshift galaxies. Of course, this changes the mass to light ratios of high redshift galaxies. And so the way we did that was to implement this non-universal IMF, or this evolving IMF, modulated by both metallicity and redshift, in a semi-analytic model that is called CAT, stands for Cosmic Archaeology Tool. It was developed by Alessandro Trinca for his PhD project, and where we use purely semi-analytic merger trees to map out the distribution of progenitor halos at very high redshift, and then we populate this with different stellar populations, accounting for all the baryonic processes that are believed to shape the properties of high redshift galaxies, so radiative, chemical, mechanical feedback. And then we also populate these early galaxies with their nuclear black holes and follow different accretion modes. And then, of course, we have to calibrate the model somehow to more local observables. And so having done that, we have checked what is the UV luminosities of these high redshift galaxies. And you see here the predicted number density of sources in the model at a UV magnitude of -20 for 3 different redshift bins. So redshift between 10 to 11, 12 to 13, and 14 to 16. So you go to higher redshift as you move to the right. And these 3 different histograms show you what is the expected number density if you consider, as in black, stars to form with a universal IMF, no changes in the stellar populations. In blue, if you add the additional contribution to UV luminosities by the central AGN. And in yellow, if you consider the evolving IMF, okay? And these horizontal shaded regions are the expected number density based on photometric candidates at these 3 redshifts, and the light green with the arrows show the predicted number density based on spectroscopically confirmed candidates, okay? So if you take the photometric candidates, you can clearly see that at redshift of around 10, the number density are consistent even with a universal IMF. But as you go to higher redshift, you need to have this extra boost, which can be provided by the evolving stellar populations, okay, in order to be in agreement with the observed UV luminosity density. If you go to even higher redshift, you see that the boost that you get from the evolving IMF is significant, but it's not enough to really accommodate the model predictions with the observation. So Particularly at the bright end, you need to have something else going on in order to, justify this low evolving bright end of the UV luminosity density at that redshift. Another way to look at that is, again, taken from this paper by Marco Castellano, is to consider all the photometric candidates between 15 to 20 and to compare this with the model predictions. Again, the pink one is for a standard universal IMF. The yellow one is for the evolving IMF. You see that you get a boost, but this is not enough to really accommodate these data points should all of these candidates be confirmed. So these, again, are photometric candidates. If all of them turn out to be interlopers, then we don't have any problem. But if at least a fraction of these will be confirmed to be at this high redshift, then we do have a problem because we really miss a large fraction of UV bright galaxies. So changing nature of stellar populations can help. It is predicted naturally by physics, but it's not enough. So you must also have additional effects going on. One alternative possibility that I will be discussing is the fact that as you go to higher redshift, you don't expect the galaxies to be chemically evolved and hence to have a significant amount of dust, which would decrease their UV luminosity simply by attenuation. So let's see what are the predicted sources of dust at this high redshift. So of course, the fact that as you go to higher redshift, you do expect to have less dust attenuation is also supported by the fact that you observe these galaxies to become progressively bluer. Okay, the metric that is generally used here is the beta slope, so it's the power law slope in the UV rest frame of the galaxies, which depends on a lot of different physical processes, including dust attenuation. Okay, and I show you here the result of a nice paper by Michael Topping and collaborators, but again, this has been shown by different authors using different set of data of what is the evolution of the beta slope as a function of the UV luminosity and as a function of redshift. Okay, so the first thing that you can see here is that if you go to fainter galaxies, typically the beta slope decreases, meaning that fainter galaxies are bluer. And if you if you consider a given magnitude beam or luminosity beam, and you plot the beta slope as a function of redshift, as shown here, you see that for a given fixed UV magnitude, the beta slope decreases as you go to higher redshift. Okay, so this altogether means that fainter galaxies and galaxies in general at higher redshift tend to be bluer, so that they have been dubbed by Ziparo and collaborators as blue monsters, because they are really very blue. Now, what is our prediction for dust production at early cosmic times? So I took this figure from a recent review paper that I wrote with Roberto Maiolino, where we were trying to summarize what is our current status of understanding of dust sources at high redshift. And you see here a very simple summary plot in which we assume that all the stars are forming a single burst at redshift 20, and then we let the stars evolve. So this can be seen as the age of the stellar population, but also if you assume them to form at redshift 20, you can see the corresponding redshift on the top. And this is the dust to stellar mass ratio released in the interstellar medium. And we consider the contribution of supernovae in blue, with the shaded region encompassing different metallicity intervals for the progenitor stars of the supernovae. And in light blue, you see what happens if you consider the effect of the supernova reverse shock. Supernova reverse shocks then encompasses the ejecta and can destroy part of the newly formed dust. And so you see that you can have a decrease in the dust to stellar mass ratio. And then after some time, you start to have the contribution of less massive stars in the AGB phase. And also we have also considered the current models, the prediction of current models for Wolf-Rayet stars and stars in their red supergiant. So what you can notice here, if you focus now on the redshift range that we were discussing before, so from redshift 10 and above, you see that you are very sensitive at very early times to the effective dust yields of supernovae, whether supernovae produce that amount of dust or what is the effect of the reverse shock destruction. So the dust to stellar mass ratio are very sensitive to supernova dust yields. In addition, you also notice that over this redshift range, essentially the time scales for stellar dust production correspond to the time scale for galaxy growth. So this is very interesting because it would offer us the opportunity to really understand the efficiency of these different dust sources at early times. So let me dig a little bit into more details on this first point. So what do we know about the effective dust yields of supernovae? So with this question in mind, with Kokyo Taki, a postdoc in Rome, we have revisited previous predictions for dust yields from supernovae, starting from a very large grid of supernova explosion models developed by Marco Limongi and Alessandro Chieffi in Rome, spanning, as you see, a broad range of stellar masses and initial metallicities here expressed as the ratio between the iron abundance to the hydrogen abundance normalized to the solar values. And then once we have computed the amount of dust that is nucleated in the ejecta of these different supernova, we consider the effect of the reverse shock disruption set consistently, assuming that the explosion takes place in a uniform density interstellar medium. So this is, again, hyper simplified. If you've ever seen the image of a supernova remnant, you know that this is highly simplified, but it allowed us to explore a broad range of parameter space. And these are the results that we have found. So here again, we are assuming a single stellar population exploding in a burst. We report here the IMF average quantities as stars evolve. So this is the dust to stellar mass ratio as a function of time. And we focused on the first 30 million years of cosmic time, where the only sources of dust are essentially supernovae. Okay? So each of these panels show a different initial metallicities of the stars that where the supernova progenitors were formed, and this figure is for non-rotating stars, and this figure is for rotating stars, assuming a rotation rate of 300 kilometers per second. Mm-hmm. The solid line shows whatever is formed in the ejecta, and the other lines show the reduction of the dust due to the reverse shock. So what you clearly see that the effect of the reverse shock is very important in reducing the amount of dust, and also that you can have dust to stellar mass ratio spanning essentially 3 orders of magnitude, depending on metallicity, rotation rate, and density of the circumstellar medium. Okay, so a large 3 orders of magnitude is quite a large uncertainty on the effective dust content of these early supernovae. But in addition, what we can also do is to, we don't only have information on the dust mass, we have information on the typical grain properties that are formed and on the grain size distribution, okay? And even how the reverse shock affects the composition and the grain size distribution of the surviving dust, typically destroying the smallest grains, okay? And so what we can do then is to fold this information and compute the attenuation, the extinction properties in these environments. So what you see here, again, for the same, with the same panel structure, non-rotating and rotating star, different metallicities, fixing the age at 30 million years, but we have, of course, the time dependence of it. We do predict what is the extinction curve expected from these grains. And now again, you have that the solid line shows what is predicted at the end of the nucleation phase, and the other colored line shows how this is changed by the effect of the reverse shock. So if you look at this panel, for instance, you see that you have a relatively steep attenuation curve, extinction curve at the end of the nucleation phase. But as the smallest grains get destroyed by the reverse shock, this extinction becomes flatter, right? However, you also see a variety of different features depending on the initial metallicity and rotation rate. In some cases, you have a UV bump here. In others, you have, a featureless extinction curve. And we have compared here the predicted extinction properties with, some well-known and widely used extinction curve, even in high redshift studies. So for instance, this is the SMC, the Small Magellanic Cloud extinction curve. The gray solid one is the Calzetti extinction wall, which is often used. And then you have in the middle, the Milky Way and the Large Magellanic Cloud one. And so you see that in general, for most of the cases, the predicted extinction that we predict at the end of the reverse shock destruction is much flatter, even of the Calzetti law. And this has important implication for, reducing the obscuration of these super high redshift galaxies and reducing also their infrared luminosities, right? So there are a number of observational implications of this. So somehow we have tried to compare our model predictions with the observations, because now with JWST, several groups have attempted to fit the spectral energy distribution using a parametric attenuation curve to infer the properties of the attenuation curve. And so remember that now we talk about attenuation curves because the geometry of stars and dust plays a large role here, which we don't have because we have purely extinction properties from our supernova dust calculation. However, you can compare these model predictions for the reverse shock models and for the non-reverse shock models that are shown by this shaded line, encompassing more or less the variations of the properties that we have found with the observations, okay? And more or less, I think that you can see, especially if you compare this with the Small Magellanic Cloud or the Calzetti extinction law, that even the observed ones seem to suggest indeed that flatter attenuation are more common at high redshift than steeper attenuation, supporting the idea that especially if you go to relatively young starbursts where the supernova dust is the dominant contribution, you could expect to have less attenuation, and hence if these blue monsters are indeed dominated by supernova dust enrichment, we could relatively easily explain their colors. But is this enough to really explain this offset, to go back to our initial question? Well, there have been models, especially in the group of Andrea Ferrara, promoting the idea that in these high redshift galaxies, you don't have dust. You may have dust, but the important thing is that the attenuation is very low. And indeed, in these models, they predict a large number of UV bright galaxies. However, as again, you see from this comparison taken from the paper of Marco Castellano, you see that these are the predictions of their model at increasing redshift. This is at redshift 12.5 and then 15, 16, and so on and so forth. And again, if you look at these data points, you see that, again, all of these candidates were confirmed to be at redshift between 15 and 20. Still, we would have, a problem in matching the bright end of the UV luminosity function. So on top of changing nature of stellar populations and on top of the fact that you expect little dust attenuation in these high redshift galaxies, you may also need something else, to explain these UV bright systems, which were, if these were to be confirmed. Now, another interesting aspect that I would like to discuss is the fact that only 200 million years later, from the epoch where we were discussing until now, so redshift 10-ish, ALMA has provided us with samples of massive galaxies which are already significantly metal enriched and dust enriched. Okay, so it means somehow that in between there must have been very fast dust enrichment in the ISM of these galaxies. Okay, to give you just a sense of how fast this is, at redshift 8.5, the Hubble time is 600 million years. And so this is, corresponds roughly to the lifetime of a 2.5 solar mass star. Okay, so this is really super fast. Now, among the many different studies that have shown, have detected the properties of, the far infrared emission with ALMA of these high redshift galaxies, I'm showing here the result of the Rebels large program, which have targeted massive UV. The galaxies were selected to be UV bright, so UV bright, massive galaxies at redshift between 6.5 and 8 point something, and detecting the far infrared emission from all of them, or most of them. And then very recently, this has been complemented, at least for a sub-sample of these galaxies, by JWST near-spec IFU data, so that we can also pin down a little bit or reduce the uncertainties on the stellar mass determination of these galaxies and also determine their metallicity, which is very important. And so, to summarize in one plot the many interesting work that have been done on this data, I show you here the result by this paper by Ido Algera, where you see different dust-related scaling relations. So this is the dust-to-gas mass ratio as a function of metallicity, the dust-to-metal mass ratio as a function of metallicity, and the dust-to-stellar mass ratio, okay? And the red data points are the Rebel sources, and the blue data points are additional high redshift sources that have been detected. Now, these are compared, you may see them with these gray dots and this gray band, which show local galaxies of the Dustpedia and additional surveys, okay? So the point that you can clearly make is that these Rebels IFU sources at redshift between 6.5 and 8 appear to populate the same region of these planes of local galaxies, okay, which is, pretty surprising. It means that they have already very chemically mature interstellar media. And of course, now we are at redshift between 6.5 and 8. You can no longer consider the grains to reflect simply the dust yields of the first explosions. The grains, once they are in the ISM, they go through a lot more complicated physical processes, And I took this nice figure from a paper by Fred Galliano, where he's emphasizing the different physical processes that these little grains can go through, going from shattering, sputtering, desorption, sublimation, but also coagulation and grain growth in different phases of the ISM. And their properties in turn affects the structure of the ISM. So it's a very complicated, nonlinear crosstalk between dust grains and the interstellar medium. And of course, this is very hard to model. However, in the past years, several groups have attempted to include at least a fraction of these physical processes in hydro simulations and cosmological simulations, including Johan here, who has done very nice work on that. And so I will show you very briefly here the result of our attempt with Dusty Gadget, with Luca Graziani, where we have included some of these physical processes, supernova, AGB, dust production, grain growth in the ISM, destruction by supernova shock, sublimation, astration, ejection of these grains in the along with the evolution of the galaxies themselves. And we have already presented some of this work in different papers led by Claudia Di Cesare and Alessandra Venditti to PhD students in Rome. So what I just want to show you here is a part of my of a result that I got here by working here in IAPE, where I try to compare now the model predictions, the prediction of the simulations with the Rebels IFU data. So here again, you see the dust to gas mass ratio and the dust to stellar mass ratio as a function of metallicity. And the different colored points are different simulations by Dusty Gadget. The gray points that you see in the background are the local dustpedia galaxies, and the black points are Rebels IFU data together with additional galaxies that have been observed at different redshift. And the different panels I have divided, since for dust physics, the range between 6.5 and 8 is a pretty large fraction of these 200 million years. I prefer to split this into 3 different redshift bins. And what is impressive to me is that these galaxies really follow the same trend of local systems, of local galaxies. And you can also, in the simulations, you can also check what is the origin of dust, what is the dominating origin of dust, and you find that at very low metallicity, this is purely dominated by stellar dust production, so supernovae, and even a tiny fraction of masses due to AGB stars. And at much higher metallicities, everything is dominated by grain growth. And this is absolutely consistent with what has been found by other authors and by the interpretation of local galaxies by Fred Galliano and collaborators. Okay? So it seems that at this early cosmic time, you will have really a very rapid metal enrichment, especially for the vast massive galaxies. This is occurring in really 100 million years of cosmic evolution. So in the last 5 minutes of my talk, I will try to convince you that, of how black holes fit into this scenario where I have been discussing, the nature of early populations and first epochs of dust enrichment and metal enrichment in the universe. And again, I show you these 2 important pieces of evidence that have come from JWST observations of these faint AGNs at high redshift. The one that we were already discussing, so the overmassiveness of these potential overmassiveness, I would say, of these black holes, and the fact that they show a very large number density. So if you look at this is in particular the UV luminosity function of these AGNs observed with JWST, and you look at the extrapolation towards the faint end of the quasar UV luminosity function, you clearly see that they are much higher in terms of number density. So they are a relevant population in terms of their frequency. And of course, if you take these two pieces of evidence at face value, the obvious consequences are that in order to justify these observations, you would expect the black hole seeds to form, at early cosmic times, to form heavy to help them grow fast. But you also need them to be numerous enough to justify this relatively large number density. And of course, you want to have an efficient black hole growth, okay? So these two things are very much, interconnected. I will, to simplify as much as possible, I will focus only on the first of these two. And of course, this brings me again back to the physical conditions that enable black hole seed formation at early cosmic times. And this has to do with the fact that you want to, prevent the star from cooling too fast. You want to have like a sort of monolithic collapse to form these heavy black hole seeds. And so you want to have a lot of UV sources to photodissociate H2, molecular hydrogen, so that you don't cool the gas, and little dust and metal content. And I've asked ChatGPT what is the recipe for black hole seed formation in the direct collapse edition. And amazingly to me, the ingredients that ChatGPT was suggesting are, I would say, pretty correct. So 10 to the 5, 10 to the 6 solar masses of pristine gas, high inflow rates, no fragmentation, no stars allowed. This is not quite true. A dash of Lyman-Werner radiation, I would say a lot more than a dash, a strong flux of Lyman-Werner radiation. And then you have to keep the gas hot and stable, let gravity work, and avoid premature star formation. I think that, it's pretty amazing. I would say that you probably don't need pristine gas. You need gas with metallicity, not to exceed a critical value. You don't need a dash of Lyman-Werner radiation, of UV radiation. You need, flux that is much higher than a critical value. You can afford to have star formation, but the important part is that this has not to be too early during the collapse, otherwise you don't allow the central gas concentration to build up a supermassive star, which is what you need to form a supermassive star before this collapses into a black hole.
I think you could get a Michelin star for that.
So eventually, everything depends a lot on these two parameters: the critical value of UV radiation that you require and the critical value of metallicity that you don't want to exceed. And this, we have shown this using semi-analytic models that, if you look at what is the mass function, the mass distribution of black hole seeds at redshift 15 in progenitor galaxies of what would become then a quasar, so a halo hosting a supermassive black hole at redshift 6, you see that the distribution that you have in a black hole mass is very different depending on the values of J-cret and Z-cret that you assume, okay? And typically, if you increase the metallicity, and if you consider different values of J-cret, you start to populate this high mass end of the distribution, which is resulting from, this direct collapse black hole. So clearly, in order to have sufficiently big black hole seed, you don't want metal and dust to exceed a significant value in these environments, and at the same time, you want them to be sufficiently strongly illuminated, and this has been shown to be possible and feasible in the progenitors of these big halos that would host quasar at redshift 6. This has been recently shown again using CAT, but this time run on n-body merger trees and body simulations by Alessandro, who here shows the distribution in this box of potential direct collapse black hole hosts. So where you see the green points is where this monolithic collapse in principle can occur given the environmental conditions. So several potential direct collapse black holes form along the way to form a central supermassive black hole in high redshift quasar. The question is whether the same conclusion would apply in a less overdense region of the universe, in a more conventional, I would say, region of the universe. And somehow, just to give you an idea of what you can find, somehow we have explored this with semi-analytic merger trees. You see here the number density, so the black hole mass function, so the number density of black holes expected as a function of their mass. And this is a plot taken from a very recent paper by Sofia Garis, a PhD student in Cambridge, who used Jade's data. She was stacking Jade data to reach higher sensitivity, and so to be able to constrain the number density at lower black hole masses where you have a larger sensitivity to the black hole seeding process. And so here are her data points, and this is compared with a large number of lines which shows different model predictions. So, but I want to show you are the blue lines which show the predictions of CAT of our semi-analytic model. And in particular, the solid line here is what we predict, assuming that the black holes can never exceed in their growth the Eddington rate, okay? And when we do that, we cut off completely the accretion from lower mass black holes because these are very inefficient, and we only have accretion onto heavy seeds. So in a way, you can take this as a proxy for what you would obtain if only heavy seeds can form, provided that they cannot exceed the Eddington rate in their growth, okay? At the same time, if you allow the black holes to grow super Eddington, then you can see that you can have a large number of black holes, much higher, because you allow somehow even lighter seeds to grow. This is very complicated. It would require a talk by itself to show how difficult it is to grow these lighter seeds. But in semi-analytic model, if you allow them to do that, even in short bursts, you can find very large number densities. And of course, not all of these black holes would be observable because they are too faint. So if you consider the fact that you only observe black holes above a given luminosity, then you see that this is the prediction, which is more in line with the observation. So clearly there is a lot to do, but perhaps having only heavy seeds is not enough to explain the observed number density unless you allow them probably to grow at least a fraction of their time very, very efficiently. So I get here to my conclusions. I think that, along this probably kind of disarticulated talk in which I've touched different topics from early stellar populations to early dust enrichment and how this, is, shaping also the environment where these first black hole form. I think I've shown you that JWST is really providing us with several pieces of this cosmic dawn puzzle, but we still need really to have a global picture. We still need to assemble them together in order to really understand what are the basic physical processes that have shaped this very interesting phase of the evolution. And I thank you for your attention. Thank you very much, Raffaella. Questions? Yes.
Thank you, Raffaella, for a very nice talk. I have a question about curiosity about the supernova models, the grid models that you use them to establish some of the yields and the impact of the reverse shock. I took a peek at the model from Marassi et al. 2019. I think that they use like a fixed energy for the supernova, and I guess that in some sense it's to be expected that that is not the case, and most likely it's going to impact the nucleosynthesis as a whole and possibly also dust formation. So how much of these aspects can impact like the
Yes, a lot. There have been attempts to investigate this a bit, always using somehow artificial explosions. So, changing the mascot as a proxy to a more successful or a less successful explosion, of course. And of course, you have a large impact, not only on the amount of dust that you can form, because you have a reduced ejecta and reduced metal-rich ejecta, but also on the kind of grains that you have. So definitely, this is something that needs to be folded in these huge error bars that you see. I would say that there are now attempts, especially in the group of Marco Limongi, to try to predict in a more consistent way the amount of fallback that you have in these explosions, and hopefully, in the near future, we would be able to improve this. The model run very fast. So if you have any grid of supernova explosions that we should consider, we are more than happy to test this and to test what is the effect on that.
Thanks.
Questions? Arturo?
Yeah. When you talk about heavy black hole seeds and I guess light black hole seeds, where would you put the frontier between heavy and light?
This is a good question, and it really depends on the mechanism that you think of, how these black holes form. So in general, light black hole seeds are believed to be the remnants of massive stellar populations forming at very low metallicity. So the remnants of population tree stars. And we still know very little about the IMF of these population tree stars, but according to the simulations, some of which I have shown you, they do not go much beyond a few hundred million years, a few hundred solar masses. So the black holes that you expect are of order of 100 solar masses, of order because it depends a lot on the mass loss, on, if these stars are in binary systems, then you have extra complications. The heavy black hole seeds that we're discussing here, they come from the collapse of a supermassive stars with masses of 10 to the 4 to 10 to the maybe 6 solar masses in some very peculiar environments. And then in between of these two, you can have the formation of intermediate mass or medium weight black hole seeds generally from dynamical interactions in dense stellar systems. So, I think that I didn't have the time to go through that, but I think that what models are showing us is that there is a whole variety of different channels where you can form these early black hole seeds, and some of these are co-spatial in the same galaxy. Okay, so you don't have a single black hole seed in a galaxy. You may have a distribution of black holes in a galaxy. And I think that this is definitely something that we need to understand better, how this reflects then in the growth of the, most or the luckiest black hole, which makes its way to the center of these galaxies and grow fast.
Thanks very much for your. You mentioned that the reverse shock in the supernovae can have important effect on the dust. I wanted to know which type of physical processes happen to this material or dust which is reverse-shook to reduce? Is it the change in the heating, changing the grain size, changing to gas or whatever?
Sure. So in general, the easiest thing that you can think is that once the so you have the reverse shock going back through the ejecta, and you heat up the gas, and the ions that are produced interact with the grains, and they spatter the grains. So the most of the destruction occurs through this way. And then only the grains which can, really make their way, they move in the ejecta and they make their way to the ISM, they, suffer less destruction. So it's the dynamics of the grains in the ejecta have an important role because, of course, the more you can kick out the grains sufficiently early, the less they get destroyed by the reverse shock. But if the grains are somehow trapped in the ejecta, the main mechanism of destruction is spattering with this, heated gas from the reverse shock. And of course, if you do spherically symmetric explosions in a constant density medium, you really simplify this process a lot because some of the grains may be shielded in higher density clumps, and this has been so there have been attempts to improve the modeling in some less idealized conditions using hydrosimulations with very interesting results. Again, the error bars, the predicted dust survival fraction change widely depending on the physics that you implement and the initial grain sizes that you use. So if you use like an MRN size distribution, then you have an answer. What we have tried to do is to use a self-consistent approach. So you produce the grains with given properties in the ejecta, and then you do the destruction on that grains. It's you need to have different attempts to reduce these uncertainties, but definitely it is still a very idealized setup.
Yeah. We'll continue on this. So my understanding was that for the models of dust in supernova ejecta, people have to rely on clumpiness in the shell to reproduce the local observable, like in Cassiopeia and the Crab Nebula. So my first question is: do you manage with your model to reproduce this kind of observation,
Yeah,
around solar masses, dust ejecta?
So what we did in order to validate the Grashev model that we have used was to compare the time-dependent dust mass with the observations. Okay, so what we do is the idea is that you nucleate the grains and you let the reverse shock go through the ejecta, and you can predict what is the reduction on the dust mass as a function of time. And we did this with several local supernova remnants, trying to start from the closest possible model for the progenitor systems of these supernovae. And in general, within the error bars, the model agree with the expected dust mass at the time of the observation of the supernova remnant. But the real problem is that, the supernova remnants are generally young, and most of the destruction takes place afterwards. So you have somehow to extrapolate further in time. But I agree that, especially now with JWST, there are a lot more observables available, and this is one of the things that needs to be done. But of course, it would require more realistic supernova explosions.
Yeah, can I just continue on this?
There are more questions. I've seen more hands.
The comparison of your extension curve versus attenuation from the observation. So I wasn't sure. Are you using really extension curve for your prediction? Or
yes. No. That's a good point. That I tried. Yes, I know. I tried to make, but it was too quick, probably. So here the shaded lines are our prediction for the extinction. Okay, so it's really, you know, whatever comes out of the supernova dust models, and we process this. At the same time, the observations are clearly attenuation curve, where the dust star geometry matters a lot. And of course, again, here we are not considering any further reprocessing of the grains in the ISM. So it's purely what comes out after 30 million years of the evolution. So it's clear that we make these points, of course, in the paper that, you know, dust star geometry, as you have shown, among others, is very important. So this, you know, these different extinction properties could probably entirely come from the same, the different attenuation properties would probably come from the same intrinsic extinction, but, you know, varying the dust stellar geometry. So you are right. The aim of this comparison is to show that indeed, even if you consider supernova dust with no further, complication on the geometry and the reprocessing of the grains, you sort of expect flatter attenuation as you go to higher redshift.
You're right behind.
No, behind.
What's faster?
Thank you so much for the wonderful talk. I learned a lot. And I wanted to ask you a question about the Rebel's sources being consistent with the local sources in terms of dust to gas mass ratio and the metallicity regime. So that's showing that even at high redshift, these sources are very chemically enriched and they have a very chemically mature ISM. So do you have an explanation for why this is like already consistent with what you observe at local galaxies, or is this still like under investigation?
So it is, as you can see, under investigation. But so I think that if you, so one thing that is interesting here is that if you use the metallicity as a cosmic clock, then eventually the physical processes which are really triggering this rapid evolution in the dust content are activated. So eventually, I think that what really matters is the way you plot these things. Okay, once you normalize this to the gas mass available and you plot them as a function of their metallicity, you are essentially saying that provided that your gas is already enriched, you start this fast grain growth in the ISM. Of course, density is also very important. In fact, there is a student now in Rome who is exploring this scatter. There is a large scatter also, as you can see. This scatter, so at a fixed metallicity, why some galaxies are able to trigger fast growth and some others do not. And it turns out that the morphology of the galaxy and the star formation history of the galaxy is very important. This was already demonstrated using semi-analytic models, but we see this also in the simulation. So depending on the kind of star formation history that the galaxy has and whether the interstellar medium is more dense, you trigger a faster growth of these grains, and you get on the relation that is shared by local galaxies.
This will also tie into like improving the models of how dust grains are growing.
Yeah.
As well.
Yes.
Thank you.
We can conclude with Gary.
I'll ask a non-scientific question, a philosophical question. So you made a wonderful studies. You made several on different topics. And so my question to you, because you had a very prudent conclusion, is that to go further, do you think the bottleneck are that we need more JWST and ALMA and other observations? Or is it that the modeling has not gone far enough on the individual issues? Or is it that we have to find a way to model the different topics, black holes, dust, star formation histories, IMFs, all together?
My diplomatic answer would be all of this.
Yeah.
So definitely, I think I'm always in favor of having as much as possible a coherent approach, because I think that now we have different set of independent observables that we can exploit. And in the future, there will be even more. Think of, gravitational wave detection. So I think that having a global picture and under control all the implications of your physical assumptions on very different scales is truly very important. That's why I think that semi-analytic models can help, because with the detail zoom-in simulations you can grasp the details, and you need to do that, but at the same time you need also something to tie different scales and different observables. But of course, we have been discussing also with Akim this now, especially lens surveys with JWST are providing a look towards less UV bright systems, probably more conventional galaxy, the bulk of the galaxy population at those redshifts. And I think that this is really starting now. So we think that, I believe that the more observations of this more normal galaxy population at high redshift will be crucial in order to really pin down the uncertainties in the model.
Okay.
I will add something, also better observations and more open-minded interpretations of results. But let's thank Raffaella again.